Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 43. It's on free body diagrams, which are what they sound like. It's essentially drawing a diagram of a body removed from its environment and all the forces that are acting on that. But before we draw some of those, I want to give you a thought problem. Imagine we have a scale on a platform and you just simply stand on it. So we figure out your weight. What do you think would happen to your weight if we angled that platform? Is it going to remain the same? Are you going to weigh less? Are you going to weigh more? What if we make it even steeper? Well, I tried this. I stood on a scale, and so this is my weight. And then I put it on a platform, and I used my iPhone to figure out that this is around a 17-degree angle, and you can see that my weight got less. And so that seems kind of magical. It'd be a great way to lose weight. But what's really going on there, you have to draw a free body diagram. So I'm the object sitting on a platform. And so we've got we've got gravity acting in the vertical. And then we have what's called a normal force. That's the force of the platform holding me in place. And so we could use that to break our weight down into its two different parts. We've got this, which is going to be the force into the platform, and then we have the force down the platform. And so you can see that this vector is smaller than this vector, and that's where it's going. But it's not magic. We could use a free body diagram just to figure it out. And so in a free body diagram, you're taking an object and you're removing it from its environment, and then you're going to label all of the external forces acting on it. And so on this object, let's say these are the external forces acting on it. Each of those arrows represents both the magnitude and then the direction of that force which is acting on the object. Now, if you look at it, the vector sum of this one's going to be to the right, so acceleration is going to be the right. And you'll save yourself huge headaches if you can always set up your coordinate system and so it's parallel. One of the axes, either x or y, is parallel to the acceleration of the object. And so let's try some of these. When you're drawing a free body diagram, we're always going to draw a free body diagram of this car. You really want to include only two things, the body and external forces acting on the body. Don't make these common mistakes. Don't include other bodies. Don't include internal forces, for example, the car acting on itself, or forces exerted by the body. And so how would you draw a free body diagram of this car? Well, we're going to have the platform, and let's say that it's stationary, and the car is not moving. And so let's draw the car. So that's going to be what the car looks like. That's the object. What forces are acting on it? Well, gravity is going to be acting in the vertical, so the force of gravity. But it's not accelerating down, and so we know there must be an opposing force, and we call that the normal force. Remember that the normal force will always act perpendicular to the object on which it's sitting. In this case, it's going to act in the vertical. Now, are there other forces acting on the object? I would say no. It's just sitting there. There's no net acceleration, so it'd be easy to set up a coordinate system like this. Now, in all of the subsequent free body diagrams that I'm going to explain, what you should do is pause the video and try to sketch them out. Then unpause the video and see if you were right. So let's try another one. We've got a car that's accelerating to the right. And I've just paused the video. It didn't stop. I've just paused the video at this point. So you're going to draw the free body diagram of a car accelerating to the right. I would try this on your own, or at least think it through. But let me show you what the right answer is. We're going to have the object, obviously. We've got gravity, which is acting in the vertical, and we've got the normal force. Get used to drawing those, especially if it's sitting on any kind of a platform. What other forces are acting on that body? Well, you want to start saying it's pushing on the ground somehow. But again, that would be a force exerted by the body, so you don't want to include that. But as it pushes on the ground pushes back on it. That's Newton's third law, and that's clearly a force on this car. And so we're going to label that as force traction. That's going to be towards the right. It's the ground pushing on it, going to the right. Are there other forces acting on that car as it starts to speed up? We're going to have frictional forces, both frictional forces of the ground and air resistance as well. And so you can see that the net vector sum is going to be to the right, so acceleration is going to be the right, and so you'd set up a coordinate system that's going to look like that. Let's try another one. Again, just the body and external forces. Now we've got a car that's just falling to earth, and I've paused it at this point. So what would be the free body diagram? Let me show you. We're going to have the object. We're going to have force of gravity down. There's no normal force here, that's why it's accelerating down. But we do have a frictional force in the other direction, so we're going to have the air resistance rather that's kind of pushing or opposing that motion. So where's acceleration? Net acceleration is going to be down, so you could set up a coordinate system like this. This would be fair. What about this? We've launched a car up and it's just kind of paused at the top of its arc. I've paused the video here. What would you draw Well, again, I've got the object, and we've got gravity acting down. Now, again, the one before this, even though it was accelerating down, and this one, it seems like it was moving up and then paused, we still are going to have a net force down, and so our net acceleration is going to be down. There's probably not frictional forces acting on it, and so that would be easy to set up a coordinate system that looks just like this. Let's start trying to put it at an angle. So now we've got a car that's starting to accelerate down a ramp, and I've paused it here. So let's draw that. Again, try this on your own first, but we've got the body. We've got gravity acting down. Where's our normal force going to act? It's going to act perpendicular to the platform, so it'll be in that direction. What other forces do we have? There's going to be some frictional forces and air resistance at this point as well. And so we could do a vector sum and figure out the acceleration, but you can see that it's going to be down the platform. So when you set up your coordinate system, you should set it up like this. Well, let's try another one. We've got a car that's hooked up and it's motionless at this point. So again, we've got gravity acting down. What else? Normal force at an angle. And now we have this tensional force that's holding it there. And we could do a vector sum of these and see that there's no acceleration, but it'd be good to set up a coordinate system so it looks like that. And so did you learn to create and use these free body diagrams? We can then use them both qualitatively and quantitatively to solve problems. I hope so, and I hope that was helpful.